Imagine just for a moment we're aboard a spaceship, zipping faster than light across the cosmos. Sounds like a dream, right? But what if I told you that faster than light, or FTL travel, could be more of a nightmare than a dream? First up, let's talk energy. According to Einstein's theory of relativity, to reach the speed of light, we'd need infinite energy. Yes, infinite. Our first massive hurdle is finding a power source strong enough to break the ultimate cosmic speed limit. Now suppose we somehow find this miraculous energy source. We're not out of the woods yet. Entering FTL could throw us into temporal chaos. Imagine arriving before you even leave. It sounds fun until you consider the paradoxes. You could shake hands with your past self, or worse, cause events that prevent your journey in the first place. And navigation? At light speed, stars and planets are mere blurs. Our current maps and tech aren't cut out for this. One wrong calculation and we could crash into an asteroid or stray into a black hole. Not exactly the scenic route we'd hoped for. Then there's the effect on us, physically and mentally. The human body isn't designed for hyperspeed travel. Think about the immense forces, the cosmic radiation. These could wreak havoc on our bodies. And let's not even start on the psychological impact. Space is vast and lonely, and traveling through it at breakneck speeds could lead to severe mental strains. And finally, let's dive into the quantum level. FTL travel might mess with the fundamental forces that hold our universe together. Could we accidentally create new particles, change physical constants, or even cause a cosmic catastrophe? The stakes are unimaginably high. So, as much as I love the idea of zipping between stars and exploring distant galaxies, the reality of faster-than-light travel might be a bit too risky, at least with our current understanding of physics. For now, maybe it's safer and wiser to adhere to the cosmic speed limits set by our universe. Now that we've explored the cosmic gamble of faster-than-light travel, let's dive into some of the most fascinating theoretical concepts that scientists have proposed to break this ultimate speed limit. First up, the Alcubierre Drive. Imagine a spaceship that contracts space in front of it and expands space behind it, creating a warp bubble that moves through space-time. This idea, proposed by Mexican physicist Miguel Alcubierre in 1994, is rooted in Einstein's general theory of relativity. While it sounds like something out of Star Trek, the energy requirements for such a drive are astronomical, far beyond our current capabilities. Next, we have Krasnikov Tubes. Picture a tube of warped spacetime that allows for a return trip from Earth to a distant star at speeds faster than light without violating the principles of causality. This speculative mechanism is still a mathematical curiosity, but it offers an intriguing possibility for future space travel. Then there are traversable wormholes. Think of these as hypothetical tunnels through space-time that could connect distant points in the universe. If such wormholes exist or could be engineered, they might allow for instantaneous travel between two locations, bypassing the light-speed barrier entirely. However, the existence of such wormholes is purely theoretical at this stage. Quantum tunneling also offers a speculative glimpse into FTL travel. This quantum mechanical phenomenon allows particles to tunnel through barriers they classically couldn't surmount. Some theories suggest that quantum tunneling could be used for FTL communication or travel, though this remains highly speculative and far from practical application. Lastly, let's talk about hyperfast solitons. Recent theoretical work has proposed the existence of hyperfast solitons, compact waves that maintain their shape and move at constant velocity. These solitons could theoretically enable FTL travel using only positive energy densities, avoiding the need for exotic matter with negative energy density. It's crucial to note that all these methods are currently beyond our technological reach and may remain so for the foreseeable future. They often require conditions or materials that are not yet attainable, such as negative energy densities or the ability to manipulate space-time on a large scale. But these concepts continue to inspire research and debate within the scientific community, keeping the dream of FTL travel alive. So while faster-than-light travel remains a tantalizing dream, the exploration of these theoretical propulsion methods keeps our imaginations and scientific ambitions soaring. Now that we've explored the fascinating theoretical concepts behind faster-than-light travel, you might be wondering, are there any experiments or observations that support these theories? The short answer is no. There have been no definitive experiments or observations that conclusively support faster-than-light, FTL, travel or communication. According to Einstein's theory of relativity, nothing can travel faster than the speed of light in a vacuum. But that doesn't mean the scientific community hasn't had its moments of excitement. One notable example was the OPERA experiment in 2011, which initially reported that neutrinos were traveling slightly faster than light. This result would have had profound implications for physics, suggesting the possibility of FTL travel. Scientists around the world were abuzz with the potential ramifications. However, further investigation revealed that the surprising measurement was due to a calibration error involving a faulty cable connection. The scientific consensus quickly reverted to the stance that FTL travel remains beyond our reach. While experiments like OPERA turned out to be missteps, they serve as important reminders of the rigorous scrutiny needed in scientific research. Theoretical proposals like the Alcubierre Drive, Krasnikov Tubes, Traversable Wormholes, and quantum tunneling remain speculative concepts. These ideas often involve exotic forms of matter or energy and are not supported by experimental evidence, but are rather thought experiments or solutions to equations in general relativity. In the realm of quantum mechanics, there is the phenomenon of quantum entanglement, where two particles can instantaneously affect each other's state, no matter the distance between them. While this spooky action at a distance occurs at seemingly FTL speeds, it does not allow for the transmission of information in a way that violates causality or the speed of light limit. So for now, faster-than-light travel remains a tantalizing dream. But the exploration of these theoretical propulsion methods and the rigorous testing of new ideas keep our imaginations and scientific ambitions soaring. If faster-than-light FTL travel were to become a reality, it would profoundly alter our understanding of time and the fundamental structure of the universe. FTL travel could potentially lead to causality violations where an effect precedes its cause. This would challenge the very basis of our understanding of time as a linear progression from past to future. In Einstein's theory of relativity, simultaneity is relative. Two events that appear simultaneous in one frame of reference may not be in another. FTL travel might allow us to witness events in a different sequence than someone traveling at subluminal speeds, further complicating the concept of a universal now. Currently, as per special relativity, time dilation occurs when objects move close to the speed of light, causing time to slow down for the moving object relative to a stationary observer. With FTL, this concept might need re-evaluation or could lead to scenarios where time could speed up or even reverse for travelers. FTL travel might lend credence to the block universe theory, where past, present, and future exist simultaneously. If FTL allows for time travel, it could imply that all points in time are equally real and accessible, changing our perception of time as something that flows. Quantum entanglement occurs instantaneously over any distance, leading some to speculate about FTL connections. If FTL travel were possible, it might provide new insights into the relationship between quantum mechanics and space-time, possibly reconciling quantum entanglement with relativity.